Uh, um, it gives me great pleasure to invite Professor Peter Clift to give his talk.
Great. Yeah.
Would you like a glass of water, Peter?
No, I probably shouldn't, but thank you. Is that the laser? Yeah, cool. Okay. So what I'd like to do is talk to you a bit about climate tectonic interactions, because I like them, and I hope that you do too. And if you don't yet, hopefully you will in 20 minutes. So I wanted to thank some of the people who'd helped me along the way. My old advisor I mentioned before, but some of the people who are really important in my career: Paolo Vanucci, now in Florence, Alex Webb, you'll see some of his stuff, and cast of characters actually going back many years. And of course, my students, my lovely students, PhD students, master's students who I started working with in Louisiana, and some of who contributed substantially to this. As Bob Holdsworth was saying earlier, is sort of, that's not teaching, isn't it? It's just having fun with your research and some friends. That's great, and get paid for it. Wonderful. So, but some of my interest in this whole topic came as a result of me chatting with Peter Molnar, Peter Molnar, years ago, one of the first people who started to link the development of climate, particularly the Tibetan plateau and the Asian monsoon. This idea that as the plateau goes up in the air and it develops this warm pool of air in the summertime that rises, it forms a low pressure system, and it draws in moist air off the oceans. This idea that the topography, the solid tectonics of the planet might be helping to sculpt the climate was something really exciting to me. In fact, if I remember this, the way I remember the conversation is him convincing me that tectonics wasn't a terribly exciting topic anymore, and that we were just crossing T's and dotting I's, and I should try something more challenging like climate. So anyway, he was to blame for a lot of this, but both generally and for me in particular, pushing me in this direction. And particularly getting interested in this type example, the monsoon, the Asian monsoon, this seasonal weather of Asia, particularly the heavy rainfall along the Western Ghats of India, the Himalaya, and of course, particularly in Southeast Asia, southern China. And as you probably know, the monsoon represents a departure from the normal Hadley circulation, where we have rising air at the equator and descending air, dry air in the mid-latitudes. If that were true in Asia, then all of these areas heavily populated now would be a desert like Saudi Arabia, and they're not. And there's a good reason for that, because the Hadley circulation doesn't work in Asia in the same way. So it's important for geology, but also for society. And since then, apart from this very simple linkage between Tibetan plateau and monsoon intensity, there's been, of course, a lot of debate about quite how that works. Some people favoring the long-term uplift of the plateau being linked to a stronger and stronger monsoon. Some others, for example, emphasizing the importance of the barrier effect that the Himalaya has in ponding hot air over the Ganges Indus floodplains and generating the low pressure area there. But generally, a lot of these studies have been essentially theoretical. They've been modeling studies, but there hasn't been, when I started to wonder about this, there wasn't a great deal of information, of field information to try and demonstrate these linkages between the solid Earth and the climate as modulated through surface processes. And so that's why I thought a geologist might be useful in looking at monsoons by looking through the sedimentary record, that lovely tape recorder that Mother Earth keeps for us. And actually, before I was even interested in such topics, people like Jay Quaid and his friends were looking at the foreland basin here in Pakistan and Northwest India, and showing this transition here in carbon isotopes, also in oxygen isotopes, in foreland basin sediments, that they link to the change in vegetation from a sort of a tree-dominated C3 flora that back here, and then in more recent times C4, more grassland, that at that time they associated with the onset of the monsoon. The monsoon's here today, so this change must indicate the start of the monsoon. And that seemed relatively sensible, because another important person from my scientific past is Dick Croon, who was hired as a lecturer in Edinburgh about the same time I was a PhD student. So if you don't know, both Dick and Peter passed away in the last year, two very important people in this whole story. And it was thanks to Dick Prune and his work offshore Oman, looking at these wonderful little the Globigerina forams and seeing how they are associated with the modern monsoon upwelling there, and how this began strongly about 8-9 million years ago. Records that were paralleled in other parts of the world, in the South China Sea and in the North Pacific. And we got this idea that something important was happening there in the late Miocene. And what could that be? It always slightly confused me because, of course, the Himalayas have been there a lot longer, since 8 or 9 million years ago. And that was one of the things that provoked me into looking into this more. Subsequently, of course, there have been more operations to look at the monsoon offshore, work here, for example, in the Maldives, in the inner sea of the Maldives. Isn't this one of the most beautiful seismic profiles you've ever seen, with this enormous drift deposit that's built up actually starting around 12.9 million years ago, that represents the start of these strong regional wind patterns, the monsoon winds. Actually, while I'm here, I wanted to say not only was Dick Prune important, but that ship behind him is. And it's a very sad year. Of course, many of you know that the ship is now being discontinued, which is really a tragedy. It was one of the most formative communities in my whole scientific career. I thank Alistair for taking me to Greece and showing me rocks there, but I really thank him for telling me to apply for an IODP drilling leg. That was a much better suggestion, even if the food wasn't quite as good. So what I was interested in actually was not only, I mean, sort of intuitive in a way. Big mountains would block airflow and push currents here and there and affect the climate. But I always thought it was one of the most intriguing things for me was the fact that this might be a two-way street, and particularly the idea that the monsoon might actually affect the mountain building and not only the other way round. And I really like this idea, admittedly not shared with everyone, but the idea that the heaviest rainfall along the front of it, this is a cross section with India going down below to the Tibetan plateau, the idea that the strong monsoon rainfall on the mountain front would focus the erosion here, remove the shallow rocks, and allow deep buried metamorphic and igneous rocks, the glucogranites of the Himalaya, to come to the surface here. This is the thing called the channel flow model. You don't have to believe in channel flow to think that the monsoon might have affected the mountain, but the idea that the climate might be essentially determining where these big faults are forming and why there's high-grade metamorphic rocks in the Himalayas and not on the north side of the Tibetan plateau, for example, was something I found very intriguing. And it was interesting then to put together data from the marine setting, things like climate records here from the South China Sea. This is based on clay mineral data, essentially with the high values, or it's flipped over, the low values coming up here to represent a peak in monsoon, starting much, much earlier, right? Not at 8. In fact, at 8, everything's coming back down again. It's drying off. The idea that the monsoon might be modulating the erosion and the development of the mountain was something I found very intriguing. So that's the South China, that's the South China Sea. It's a clay mineral, it's a weathering related proxy. Meanwhile, on the other side of Asia in Pakistan, the Indus Delta was looking like this, pretty darn similar, with a reducing chemical weathering up until the present day. And indeed in the Bay of Bengal here with a reduction here. So a peak period in the mid-Miocene when the earth is hot and then getting cooler and drier as we go into the Pliocene. And this actually correlated with, again, with seismic data, seismically produced sediment budgets that showed peak erosion, this into the Indus submarine fan, peak erosion during the Middle Miocene, and a reduction. So there would be this idea of a coupling there, that the stronger the monsoon is, the faster the erosion, the faster the sedimentation offshore, but also, of course, the faster cooling in the mountains. And that actually correlates also with argon data, looking at the peak of cooling in the greater Himalaya being in the mid-Miocene and then a reduction afterwards. So this seemed to be quite an intriguing idea and something that we followed up again subsequently with more scientific drilling, of which I'll come to in a little bit. I then, because this does beg the question, is if the monsoon does start to become more powerful in the early Miocene, why? I mean, most people think that India and Asia smooshed into each other 50, maybe 60 million years if you're feeling feisty. So that's a big gap, isn't it? Between like 50 and 23. What's wrong with the mountains? For 25 million years, they're just kicking around doing nothing. That seems weird. Taiwan does not have this problem. It's young and it's having a great effect already. So what's going on? So we looked at this a little bit with my friend Alex Webb, looking at the potential of the break off of the Himalayan slab, the Indian slab, in causing rapid uplift. And this is a little cartoon where essentially this is supposed to be India, with Asia, the being invisible. The blue line here is the peak of the Greater Himalaya. And the idea here is that the tearing of the slab, removing this heavy weight and allowing the Indian plate to rebound, pushing up the Himalayas rather rapidly at, yeah, you guessed it, starting around 23, 24 million years ago. And we see younging in things like the age of magmatism related to the tear, of the age of the faulting, of the motion on the main central thrust. Here, since I'm a sedimentologist, I was interested in the effect on the foreland basin, looking at things like zircon fission track and detrital muscovite argon. And so what we're trying to show here in this dreadfully complicated figure here is the fact that the red colors here, they represent the Western syntaxis over here, and everything essentially younging from the syntaxes, particularly from the west, though, into the center of the origin. So the micas are being, the rapid cooling occurs earlier at the syntaxes and then youngs into the center of the mountain belt. So then the idea would be that the popping up the Himalaya is what is causing the monsoon to intensify in that early Miocene period. So this was all very exciting, and the foreland basin is a worthy and splendid thing. But as I was saying earlier, looking at the marine records and particularly the drilling that we were able to do, particularly 5-6 years ago, oh, whoops, time flies, more like 7 or 8 years ago now, with JOIDES resolution around the marginal seas of Asia was very important. And I in particular was involved, of course, with the Indus submarine fan, but the Western colleague of its big neighbor, the Bengal fan, still about 5 million cubic kilometers. And we had some nice seismic data here. This was interpreted by one of my best PhD students, Jerome Calvez, when he was in Aberdeen with me. And we were able to drill here on the edge of the submarine fan here in the Lakshmi Basin, offshore Mumbai, essentially. And so there is a long history about the monsoon and the erosion we've been able to disentangle. I just wanted to show you one of the more interesting little tidbits. So we were able to use zircon dates, uranium lead zircon, here for the different ranges that can constitute the source regions here. And this is a sort of a method that's been used in many places. I have to say, once you've worked in the Western Himalayas, this is like the Rolls-Royce edition of provenance studies, because it has so many different and diverse source terrains, which all have their unique signature. The Greater and the Tethyan Himalaya are rather similar to one another. The crystalline Lesser Himalaya are much older, and then things like the Karakoram and Nanga Parbat in the Western syntaxis here have this very young distinctive ages. And this makes it really easy to pull apart the erosion history through the geological record. So if you've not seen these things before, this is called a probability density diagram or kernel density estimate diagram. And what that shows is basically a fancy histogram. So where you get a big peak, you have a lot of grains of that age. And they go back an awfully long way. So although the Himalayas themselves are very young, the grains that constitute this, there doesn't make much crust. The Himalayan orogeny just reshuffles things around. It doesn't really build a lot of new crust. And what we saw was that these are the sediments at the top here. These are the various source terrains at the bottom. And what you can see is, well, you'd have that little young spike here that correlates essentially with the Karakoram and bits of Keristan there. But you can see that actually the amount of Himalayan material, the 1,000 1 giga-year peak here, actually is not terribly prominent until quite high up in the record. And the Lesser Himalayan peak is really young, really young. It picks in here at actually only about 2 million years ago. And I know that several of my geological friends were not very happy about that result, but I was pleased to see that in some of the reconstructions that Alex Webb did, that he shows that here in the pink, the Greater Himalayas are buried at about 5 million years ago and are coming to the surface, well, what do you know, about 2 million years ago. So that this sort of joining up of the how we can put the sedimentary record and the tectonic record together is one of the great strengths, I think, in using sedimentary geology to solve climate tectonic problems. Now, just to round off here, I did want to note that we have been worrying much more recently, and things I'll be doing at UCL now is worrying about how all this mountain building and erosion is affecting or has affected global climate, and particularly, of course, CO2, greenhouse gases. And you might ask yourself, what on earth has that got to do with anything related to mountain building? And of course, the way that they're linked is because the breakdown of silicate rocks sucks CO2 out of the atmosphere and fixes it as carbonate into the ocean. So it has been believed for a long time that mountain building and increased weathering would cause global cooling. And there is good reason to believe that is the case. Most recently, again, one of my PhD student, a former PhD student, Tara Janelle, who works in Glasgow, University of Glasgow these days. And we looked at records from around, actually from the South China Sea, from the Pearl, the Mekong and the Indus River systems. And what we were able to show was essentially a reduction in chemical weathering through, this one's pretty flat, it's a bit reducing over here, and the Indus reducing through time. So that's less chemical weathering, whereas what you'd really want is more chemical weathering if that weathering is causing the long-term cooling of the Earth during the Cenozoic. Because that's just the degree of alteration. That's not the same thing as the flux of CO2 out of the atmosphere. We were able to calculate that too, with the Pearl being remarkably flat, the Mekong reducing modestly, and the Indus reducing quite substantially. So the increase that we would expect if the Himalayas are causing the problem isn't showing up. And that may be because other parts of the world are doing the heavy lifting for them. Places, it has been suggested, for example, that weathering and erosion in the maritime continent of mafic, arc and ophiolite units in tropical regions has been associated with glaciation in the past. The present glaciation, the last, since the onset of Northern Hemispheric glaciation, but also in the past in the Ordovician and the Carboniferous. And that's something that's going to be the focus of my ongoing work. So, yeah, just to briefly conclude here, then, what I am interested in is also the fate of these plate tectonic cycles in controlling the carbon in the atmosphere and as preserved in the geological record. So here we have a balance of carbon in and out of the Earth's mantle over long periods of time, millions of years, tens of millions of years, to which the sediment is a significant portion, the sediment being subducted into the global subduction system. And so, actually, let me skip through that. So the sediment that's being returned to the mantle is a way of stuffing carbon back to depth and potentially removing it over large periods of time from the crust and therefore from the atmosphere. So yes, one way that we can get rid of carbon is to subduct sediment. And the estimates we have of how much sediment is being subducted globally, which is about 1.7 cubic kilometers per year. That's good. The eroded forearc basement is not much use, but the dissolved river load, which is then put into the altered oceanic crust, is a way of getting rid of carbon. And then, of course, crashing passive margins into subduction zones and breaking off the slab is another good way of doing that. So I tried to estimate how fast all that was going and whether that might be significant, looking at all the IODP and ODP, DSDP drill sites going into the global subduction system worldwide. There are, of course, some sketchy bits. There were really no good drill holes for the Makran. There are desperately few, actually, along the Indonesian arc as well. What do we see? Well, I divided up here all the big trench systems here into tectonically erosive versus accretionary. And what you see here, the different types of carbon being subducted, inorganic carbon, in other words, limestones, dominate greatly, but over organic carbon. The organic carbon appears to be more important in the accretionary margins, but even there, they tend to be dominated by the subduction of carbonate. And so, let me skip through that one. So the punchline here is that the subduction of inorganic carbon in steady state subduction systems, i.e. not collisional systems, is the dominant flux of sediment back into the mantle. followed by the organic carbon here. You can see in the collisional settings, like things like the passive margin of India under the Himalayas as being relatively trivial in the long-term Cenozoic budget. And so if we come back to look at that budget I showed you earlier, where they were estimating 13 to 23 gigatons per year being subducted, that actually when we were able to revise that up substantially to about 60. And that's important actually, because in the earlier budget, the Earth was essentially in a state of steady state. But if you ramp this up to 60, then suddenly you're not in a steady state anymore. In other words, during the Cenozoic, we've been stuffing far more carbon back into the upper mantle than has been degassed through the mid-ocean ridge and arc systems. And that means less carbon to be put into the atmosphere, may be important in driving the long-term global cooling that we see since the Eocene, essentially. And now I was going to show you a bunch of conclusions, but nobody likes to read them anyway, especially not on a prize day. So I thought I'd just end with a mountain with a lot of rain on it. And thank you for your attention.